Engineering. He is currently the technical director for Jacobs Asia Pacific region, looking after mine tunnels and rock engineering projects. He has been involved in broad range of projects varying from major infrastructure civil projects to complex, deep and highly stressed underground mines. Currently, he is the tunnel design discipline lead for the Sydney Metro West Central tunneling package in Australia, but also working in the Hinkley Point C offshore tunnels in the UK and assessing Jacob's team, acting as independent checking engineering team on NEOM lines tunnel in KSA. Besides being a professional, he is also heavily involved in academia, research and development with over 60 technical publications in international journals and conferences. On behalf of Tunneling Association of India young members, I welcome you once again on our platform for sharing your knowledge. Over to you, Dr. Oliveira.
Thank you very much, Ruchi. And I've said this before. I'll just repeat to those who joined recently. So I appreciate you taking your Saturday morning in India, for those who are in India, to join this presentation. Those who are outside India also obviously appreciate your time. I can see a couple of friends here from Australia, so taking the Saturday afternoon as well. So thank you for the invitation. Thank you for time here and listening to a little bit of what I have to say and my experience. So I'll just start sharing my screen here.
Yeah, sure.
I'll just make sure that, because can everybody see the presentation? And
Yes,
confirm to me, Rishi? Okay.
yeah, it's visible. Just a small quick announcement. So if anyone has any doubts or queries, kindly post it on the chat and we'll be addressing it after the webinar. Thank you.
Yeah,
Over to you,
thank you.
Doctor.
No, thank you very much. Yes, I might not, if you try to ask something or raise a hand, I might not be able to see because I only have one screen here, so I won't probably be able to see. So if you hold to the end, if you post it or to the end, I'm more than happy to. We should have enough time. I try to make this presentation maybe only for like 45 minutes. So we should have, another 15 minutes for questions and any questions that you may have. So when I was invited to present to the young members of the Tunneling Association of India, they asked me, "Oh, can we please, David, try to find something practical, something related to a project?" And I thought I could present something that we have been developing and working quite a little bit in Australia, which is the use of high performance fibers for permanent sprayed concrete linings in road tunnels. So in particularly in Sydney, we have the practice to use our primary support, tunnel support, as a permanent tunnel. So we wanted to develop a high quality product, and we looked how to improve that with better fibers. So what I'm going to show here is actually a product of also research, but it has been applied in practice. And I'm going to show, how we develop these and what are the results, what are the benefits. And I'm going to go through some of the basics and fundamental theory as well, just to bring everybody to the same page so we can understand a little bit better. So in terms of the presentation, I divide into these sort of 6 main parts. So we're just going to have a look at what do I mean with the tunnel lining design for hard rock tunnels, for the support of tunnels in hard rock or in good quality, or sort of fair to good quality rock. The journey that we experience here in Australia in some of our projects, and how we develop how we improve the performance of the shotcrete linings using some of these tunnels. And we're going to present some of the analysis and studies that we have done to investigate how we could achieve this high performance, and also some of the field scale testing with back analysis of results. And we're going to conclude the presentation with a summary and remarks from those conclusions. So, looking first as the lining design concept, so everybody have a broad idea what we're talking about here. We will assume that the majority of people here have some tunneling background or some understanding. So I'll assume that some of the most basic comments you have you have an idea. But if you don't, please just hold your question, put your question, and we try to answer at the end. Okay. When you talk about the design of shotcrete lining design in rock, it's still today one of the most common practices, and maybe more in mining than in civil, but even in civil, is to first look at empirical design. It's a great tool, empirical design, very practical, and as a great starting point, right? So as here is a graph that most engineers involved in tunneling will be familiar. It's the Q system support chart. So what it tells us here is that if you have some good mapping and you can identify the quality of your rock by the Q index, which is the value of Q, you can, depending on your span here, you can just find in this chart what would be the practical support applicable for that tunnel, for that span, and for that rock quality. Just as an example, say, let's just for the sake of an example, let's assume that we have a rock that has a Q value of 0.4 here, and we are looking at a tunnel that when applied the ESR, which is similar to a factor safety, when I apply this FF, say we are looking at a span close to 20 meters, which is quite a large span. But for us in Australia, here's a quite common span for road tunnels. So for example, if you look here, 0.4 and 20, the bottom chart would be indicating that we would need, a shotcrete lining that is probably closer to 150 millimeters or 15 centimeters, okay? And this would be required with a rock bolt spacing of 1.5. So that's an initial guidance. The disadvantage of using the empirical design method is quite straightforward, is that it doesn't necessarily tells us if we are compliant with international codes, for example, with local codes. It doesn't tell us much about factors of safety. It tells us that this has been used and the tunnel remains stable because this was developed based on experience and these tunnels remain stable, but it doesn't tell us how safe these are. If these meet current standards, if these meet local standards, for example, in terms of safety factors that might be different from different countries, right? And also it might be different for different requirements, or may not even meet specific project specific requirements. So it's a good starting point, but generally it's not a method that's acceptable on its own. Great starting point, great in guidance, but it's typically on its own is not something that's acceptable. We still need to demonstrate from engineering principles how we design this lining. So, but sometimes, particularly in mining, sometimes this is the only design that's done. But we want to develop that further, and we moved a long way. So the second most common approach is to do numerical modeling, right? Numerical modeling, then you can obviously bring some of these codes aspects, so you can do a numerical analysis here. So for example, this is an example of an analysis where we have 3 tunnels, and we have actually is beside a cavern here, quite large cavern. And then when you analyze these, you can extract the information from your model, how the shotcrete has been loaded, right? So you extract the points here, all the axial forces, all the bending moments, and you can plot in a chart, where you apply your local standards, reduction factors, and load factors, and you see if your capacity, if your loads here are within the capacity of your shotcrete or your sprayed concrete. So for example, here, we see that there would be minor points here that will be exceeding the plane shotcrete curve here, but it's all inside the capacity of a fiber reinforced shotcrete here. Okay, so in principle would satisfy code requirements because you'll be applying reduction factors that will be defined in your code. You'll be applying load factors that will be defined in your code. And you can actually, from these, you can actually extrapolate from other structural requirements. The disadvantage here is that it can be sometimes time consuming. And what we generally want is that you don't want to be rely purely and entirely only on numerical modeling for a couple of reasons. One, it's always good to have second means of checking. Right? Two, even with numerical modeling, sometimes we are not able to cover all possible scenarios. So simple analysis are very beneficial and very welcome. And that's what I want to proceed on now to demonstrate a simple analysis that when combined with numerical modeling makes your understanding of the shockwave lining design a lot more robust and a lot more complete. Okay, so to do that in how to design, just not rely on a numerical model, which also has obviously a lot of assumptions and a lot of things behind it. I want to develop now a simple model that represents how the shockwave performs in a tunnel, in a hard rock tunnel, where the shockwave is supported or works in combination with rock bolts. So let's move on and let's have a look what it means. So when we look thinking about a hard rock tunnel support, now the first question that we have to ask ourselves for any support development is, what are we designing against? What are the failure mechanisms that I want to look at? There might be many, but we will look here the failure mechanism of the shockwave alone in this particular case. Okay, so when you're looking at hard rock tunnel, obviously we are worried about the global stability of the tunnel and also the stability of individual rock blocks or rock wedges that are developed around your opening. So here's an example here. So if we have open a tunnel here, we're only showing a portion of the tunnel. So this is a portion of, say, the crown or the roof, a portion of your crown. And if you do nothing, you'd have wedges falling out. If one wedge falls out, and it might actually bring further failures, because you'll be actually starting to unconfine other wedges that were not originally confined. So for example, here, if wedges F and C fall out of your crown, then you might start destabilizing wedges A and B, which will fall out, and then consequently E and D, and this could actually progress to a larger failure. So you want to make this stable. How we do this in rock tunneling is, for this type of failure, here we generally add the rock bolts, right? So we would be adding rock bolts here that will be tying wedge F back to a better rock, and we'll be adding a rock bolt through wedge C, which will be holding it back. Okay, now you could ask me, okay, David, we stabilize F and C, right? And we put them at a certain spacing that, for example, the spacing that was recommended by the Q chart, the Q system support, say 1.5 meters as per my example. What happens with the other wedges in between? So for example, wedge type A could still fall. Okay, one could say, all right, I can add more bolts, right? Reduce the spacing here, so maybe to make it to 0.75. Or obviously, if I want to rely on spot bolting or provisional bolting, we can also add just an individual bolt where I map this, okay? But the reality is that if we start putting the bolts at too close a spacing, we start to lose lose sight of the economical side of your support design. And you also, if you start to rely on spot bolting, you're also putting a heavier reliance on people to be really able to map this accurately and not miss this during design. So how do we address this? We actually design the shockwave to be supporting wedges that might be formed between your pattern bolting. So for example, if you're doing a pattern bolting that's 1.5 meter centers, like proposed by the Barton system, what may happen in between is what you want your shockwave to be designed against. So we want to, if the rock bolts are holding F and C here, and also obviously holding the shockwave here, I want my shockwave be able to span between these two rock bolts here and able to take this load of wedge A. Because if I support wedge A, it will key in wedges B, D, and E in place. So all I want to do here is to hold back the wedge A, such that by holding it back and with the stresses that will develop around our excavation here, it will key in all the other wedges. And that's the main principle of key block analysis. So we identify key blocks, right? And some we have supported with rock bolts, and others we are supporting with the shotcrete. So our shotcrete here will be designed for a load coming, for example, just as an example, obviously, of this wedge type A. Okay, so now that we more or less understand the failure mechanism of the shotcrete, so the rock bolt is obviously is a different topic, but so we are focusing on shotcrete now. We can understand how it works, right? So the shotcrete here will essentially be spanning between, sorry, the shotcrete will be essentially spanning between the rock bolts, supporting a certain load that develops in the middle here. How do we estimate these loads? Well, we can assume, based if you know your geology, if you know your rock system, for example, you can do kinematic block analysis, say unwedge, for using a program unwedge, for example, right, and identify the potential wedges that might be forming between rock bolts. Or you can even just assume geometrical characteristics here. For example, if you assume that it's unlikely that I have joints here that might exceed a certain deep angle or a certain fracture system, for example, say 6 degree, you can also, just by geometry, identify what type of blocks might be forming within this space. So if we move along now, okay, now I know what I have to design for, but how do I design against, well, no, design against, how do we design against this? And we start to look at similarities, right? Similarities of how this system is working. If we think here that this system looks very similar to a slab on columns, so essentially I have here rock bolts that work as concrete columns, like in a building, right? And I have a shotcrete here that works like a slab in a building. So it's just upside down in comparison to this side here. So for example, this is a picture of a structural code, right? Just putting as an example here how we can design slab on columns, where you design for the loads that are between the columns are taken by the slab, and these are transferred to the columns. And the same thing here, this load here will be taken by the shotcrete and will be spanned and transferred to the rock bolts on the side. So very similar design. So we can use this principle that we of designing as similar to a slab on column design, where the rock bolts is our column and the shotcrete is our slab. When we look at how to design against this, so we can use simplified methods, right? And one of the simplest method that's actually present in many structural codes is what we call the direct design method. The direct design method is very simple. Actually, if I go back here, all it assumes here, it assumes that this slab or the shotcrete between the bolts is actually simply supported on both ends. So so you can calculate it as a simply supported beam. But recognizing that it's not really simply supported, it is continuous. And if it was only simply supported, you would only have a positive bending moment. Those codes recommend a certain percentage that you translate that simply supported bending moment to a equivalent continuous slab. So essentially all we do is we calculate the bending moment for a simply supported beam, and we translate by a certain percentage, which is this amount here, which may vary between codes. For example, in the code in Australia says that this is about 65%. So when you translate, then you move the bending moment curve a little bit down, and you generate the negative bending moments at the supports or at the rock bolts, right? So this is how the method is. And this method was very simply addressed and presented in a paper that we use very often here for design, which was presented by Barrett and McCreath. This paper was published in 1995. I forgot to put the reference here, but I'm more than happy if anyone that later wants to contact me to know what the reference is. I'm more than happy to provide. It's a very simple paper, and that paper focus on this simple design method, the direct design method, and then highlight when looking at the direct design method. For shotcrete in particular, there are 4 failure mechanisms that we need to address and satisfy, right? So the first failure mechanism is adhesion. So when we spray shotcrete or spray concrete Obviously, we want it to adhere to the rock, to bond to the rock, right? And if we typically want that bond to be strong enough to not fail. So the first failure mechanism is adhesion. If the shotcrete is well adhered, is well bonded to the rock, the next possible failure mechanism is direct shear. So if you have a load, they can actually shear off, right? Completely, it's a complete shear failure, shear off the lining, just like this picture here. So there's a direct shear failure, and this is only possible if you have a good bond, if your bond does not fail, right? If your bond fails, then this direct shear here is no longer possible, because the way the shotcrete will be working is it will be working in a different way. It's no longer bonded here, so it cannot shear. What we'll be doing if this wedge is pushing the slab or the shotcrete down here, it will be putting your slab in bending, right? So your next two failure mechanism possible, if adhesion is lost, if bond is lost, is a flexural failure or a punching shear failure near the support, near the rock bolts. Okay. The the decision on relying on your bond capacity or adhesion in the long term is a question that needs to be addressed in every project. Due to concern of losing that bond due to potential deterioration of the interface between the shotcrete and the rock, here in Australia, we have moved to a state where we can rely on adhesion and bond for short-term temporary stability, but for long-term stability and long-term design, we have to assume that the shotcrete debonds, and we can no longer rely on that adhesion capacity or that bond capacity, which means that we always have to design the shotcrete to satisfy these two failures mechanism here. Why this is important to understand? Because if you can rely on adhesion is only a property of the interface, right? So you can understand and probably visualize that if it's only a property of the interface, how well the shotcrete has, I will use this term, glued to the rock, you can understand that it's independent of thickness, right? So if you can rely on adhesion, it means you can generally have very thin shotcrete lining because you only rely on the interface. What will be governing or your thickness here, if you have good adhesion, is the direct shear. Okay, but if you cannot rely on adhesion in the long term, then you're going to be relying on, you're going to have to design for flexure, and we know that for designing for flexural strength, thickness is very important. Like the depth of a beam is very important to its flexural capacity. So that's where thickness, so that's why that understanding is important. So when you're talking about unbonded lining design, which means that you assume that over time you're going to lose the adhesion, those are the two failure mechanisms we need to design. And because we work with flexure, flexural capacity and shear, we need to then develop shotcrete mixes and concrete mixes that have good flexural resistance, which is what we're going to move now to understand. So how we understand flexural capacity in shotcrete design, it's what we will very soon, very shortly, have a look. There's only one thing that I want to highlight here, and this is just a preamble, just a bit of a hint to the development that we did and the research that we did here in Australia, how to better design our shotcrete linings. Is that this simple design method, as I said, it assumes the lining or the shotcrete as a slab or as a beam that's calculated as simply supported, right? And then there's just a translation of the bending moments to account for the continuity. So it's essentially relying on a pure bending capacity, just like we do with beams. Okay. But because of that, it ignores, although it uses this empirical factor to translate the bending moments applicable, it ignores that the shotcrete or the line is fully continuous, and it ignores that if the lining is deforming, like I have in this picture here. So if I put my pointer here, if we have the shotcrete deforming like this, and the shotcrete say cracks in 3 points, right? If it's bending, the tendency is this shotcrete will crack in 3 points. One crack, one big crack close to the support. The two cracks close to the support, one on each side, and one central crack here. If this line is deforming like this and has these cracks, it will generate internal forces, internal compression here, that will be beneficial to the bending capacity of this slab. And this is what we call in structural design compression membrane action, which is what you see here. So using this direct design method, you would be ignoring this effect. And this effect here was also well studied for slabs. So this is not something that we developed from a tunneling point of view. This also has a good background from a lot of structural research, and how things develop. The benefit here is with this compression membrane action. For those who are familiar with the capacity diagrams, right? If you have axial forces developing in your lining, it means your bending capacity increases, right? So this was the piece that was missing, and then we started to investigate how to take that into account to make the most of the capacity of our fiber reinforced shotcrete lining. So I'm going to go later through the research project that we have done and how we tested, and this has actually been used in a real tunnel project here, and it's now being used since then. So as I was mentioning before, obviously, if we are relying on the shotcrete here as having structural capacity in bending, we need to satisfy that it can take that deformation. When we think about how the shotcrete is working here with this load coming from wedge A applied to the slab here, a lot of engineers defend, and I actually fully agree, that the most representative testing that we can do with the shockwave to represent this condition here is the toughness testing, right? So there are different methods. There's the ASTM one, which is a round determinate panel, and there's also a square one, which is the most common one is the FNAC one, right? Why this is most representative? Because you can see where the load is applied here simply represents the reaction forces of the bolt, right? And everything else is deforming around it and it's pushing. So you imagine that the wedge is somewhere outside here and it's pushing the shockwave up here, and your rock bolt's resisting. So this deformation here represents your rock bolt. And then so it's more or less representing the failure mechanism that happens with the shockwave around the rock bolt. So which is very which is very reasonable, like, to make this comparison. There's only one problem with this test, although it represents really well, and it's typically done with thickness that are of similar order of magnitude to the lines that we use. So for example, this panel here is tested with a 75 millimeters panel, and in shockwave for rocks typically will be in that order, 80. For example, the Norwegians established that a minimum thickness 80 millimeters, so you'll be working with 80, 100, maximum 150. So this is representative. There's one problem, is that what we measure in these tests is what we call toughness or energy absorption, right? So we apply the load here, and we measure deformation until this sample, has preset deformations. If I move this up here, has preset deformation, and what we do here is we integrate the curve under this, and because when you integrate load versus deflections or displacements, what you get is an energy, isn't it? So we are calculating here, obtaining from this test, how much energy this shotcrete is absorbing as it deforms, as the load is applied. So that's the output of this test. And the main problem is that there's no defined method on how we can use energy in resistance of structural elements. There's no code that will tell you, well, look, you can get the energy at say 5 millimeters deformation and apply it in this equation here or in this way. Such a method analysis, and that's why, although it's very representative, it's not a test that we can actually use directly in design. There has been ways. There has been ways around it. If I can move here, so for example, there's a few studies there, and one of them is a study by Stefan Bernard here in Australia too. But there's studies by Ada on how to convert the values of the round panel determinate from the round determinate panel. And the reason why in this particular case it has to be the round determinate panel is because the test is determinate. The FNAC is indeterminate, so there's no way of us analyzing the failure in a determinate way. So it has to be round determinate panels to use this procedure here. There's methods to convert the results, the test results from the round panels to an equivalent flexural resistance, right? Which is the next topic we're going to be discussing. So this is based on conservation of energy again and using yield line theory. So these are some equations. I'm not going to go into details here, but there are ways of calculating. Why? Because we can, based on conservation of energy here in yield line theory here, so we establish the way that the panel fails, and we know that round panels always fail this way. It always fails with 3 cracks, right? We can actually calculate an equivalent flexural resistance for a specific crack width that we have to design for. And this is how we can actually connect the results of a round panel to the results of another testing, which is the next one we're going to show, the beam testing. And if we calculate here, he's just demonstrating here that calculating the results from this round panel had a very good match from the results of the beam testing, which is a test that directly gives you the flexural strength. So you can see here the points of many different tests here are approximately, it's never perfect, obviously, are approximately sitting on a one-to-one curve, right? So he's plotting here the results calculated by this method against the results that are obtained by another test method that gives you directly the flexural strength. So as I mentioned, the test that gives you the direct value of flexural resistance is this beam test. Right? And this is a test that's simple. It's simple to estimate, and that's why it's simple to define a flexural strength of this beam here, because it's also determinate, right? And it is a simple beam that's generally if we are following EN 14651 is a 3-point bending, right? So and what we get is a curve that is load versus crack mouth opening displacement. So how much the crack opens at this location here. And so this gives the straightaway residual flexural strength, which is a strength that's then described in most, if not all, structural codes. So you can actually use the structural codes and structural guidelines such as Ryland, the Fib model code 2010. You can apply these values here directly. So you are following structural codes, so you'll be in compliance to codes, and you'll be satisfying compliance to those codes when you're using this test. So this test gives you five thresholds, right? The first one is what we call the limit of proportionality. It says when you load the sample here and you exceed the elastic capacity of the concrete and it cracks. So it's actually, essentially the first crack opening here. Then you have different values of the capacity at different crack width, right? So we have at a crack width of 0.5, crack width of 1.5, 2.5, and 3.5. And these are called different names when you get the results. So when you use the load to calculate the flexural strength at a crack width of 0.5, we typically call these FR1. So it's the flexural is a residual flexural strength at a crack width of 0.5. It's called FR1. At 1.5 will be called FR2. At 2.5 will be called FR3. and at 3.5 will be called FR4. So serviceability limit states would generally be in the vicinity of the FR1, so equal to or slightly lower. And typically limit state design will be between FR3 and FR4, depending on which code you use. So if you use Fib model code, you're going to be using FR3. If you use Ryland and some other guidelines, you'll be using FR4. So that's important. That's important to understand. Okay, now that we had a bit of a brief introduction to the concepts behind it, let's understand what the challenges that we face and some of the issues that we face and what we have learned in the process. The first thing is obviously to try to understand what values we want to achieve with our shotcrete. So we can compare, although they are not, as I said, not directly related, we can compare the results of the toughness or the energy absorption testing with beams, right? So some guidance, a lot of the guidance are towards toughness when it comes to rock support or tunnel support, because there's a lot of experience in the mining space, and this is more typical, of the in mining industry to be using toughness, to be specifying shotcrete in terms of toughness rather than in terms of residual flexural strength. So generally, when you are in a tunnel where you expect low deformation, you don't need great energy absorption. The deformation is small, you don't need to absorb a lot of energy. So typically, this is a very typical value adopted in mines here in Australia. You typically work with a 280 joules, which is a measure of energy, at 40 millimeters deflection using the round determinant panel. If you're in moderate ground, where you expect moderate deformations, you're about 360. And when you start getting higher deformation, typically at 450 or higher. Okay, so this is for areas of high deformation, sort of towards squeezing ground or towards higher stresses. So it's typically work like this. In fat to good quality rock in shallow conditions, generally you don't need to go that high. You typically be working towards this 280 or even 360 maximum. However, if you really want to specify a high performance shotcrete, you obviously and you want to improve, you want to have that sense of as safe as possible, as practically possible, you'll be working with high energy absorption. So for example, the local transport authority here in Australia, in Sydney, the Transport for New South Wales has a specification for shotcrete. It's called specification B82. It requires a minimum toughness of 500 joules, which generally we don't need from the point of view that the rock doesn't deform that much, right? But this is what they specify. When you look at 500 joules, and based on experience and also based on those, even doing those calculations that I showed to you, how to convert the results from round determinant panel to beam testing, we expect that for 500 joules, we need to be achieving residual flexural resistance in terms of the FR4. So remember the graph, the crack width of 3.5. around about 3 MPa or greater, right? So this means, as I said there before, in the beam testing, this will be a deflection of 3 millimeters, which will represent a crack mouth opening of 3.5. Okay, so this is a quite high performance shotcrete, right? And obviously you can say, David, why were you going so high performance? Well, first of all, this is a requirement of the transport authority here. But if we are to use this high performance, then we make the most of it. We want to then obviously, if we can use this high performance, we can perhaps reduce the shotcrete thickness, right? Because now I'm using a shotcrete that has higher flexural capacity. So I want to make the most of it. So at about 2014, 15, there was the start of a big tunneling boom in Australia. We're still going through it. There's a lot of tunnel projects going on, but it started at about 2014, 2015, and this is where we started also having to try to follow these 500 joules, and as a result of that, we were targeting that 3 MPa. And I'm going to show it to you what happened when you said we specified concrete that shotcrete that had to satisfy a residual flexural strength FR4 of 3 MPa. So we used a very good fiber. Is by no means is a poor fiber, which was a end hook fiber, which had a relatively high strength of 1,345 MPa. This end hook fiber here, and we used a dosage that are very reasonable. Say we started with 35, but we went from 35, 40, even 45. And what we're going to be seeing here is that even with this dosage of 40 here, for example, and we even tested 45 too, we could, as an average, achieve the 3 MPa flexural strength for FR4, which is that C mode 4 here, as an average, right? But as most structural engineers will know, we can't be designing for average values, right? We want to achieve characteristic values where we have 95% of our results exceeding the value that we specify. And there was a lot of work. We as I said, we went all the way up to 40 here, and we wouldn't, with this fiber here, we wouldn't achieve. Right, and there was a series of there's 2 projects that use this fiber in a row, and we couldn't just achieve. That meant that we couldn't take the benefit of reducing thickness, for example, because we could no longer rely on a residual flexural strength of 3 MPa that we wanted. So we had to demonstrate that our shotcrete could work with strength that was, in terms of characteristic values here, even as low as 2 MPa. So it's a big drop from 3 to 2 MPa. So we had to satisfy with 40 kilos that we had to design for 2 MPa. And you can see here with 2 MPa, I have only 5% being below, and I have 95%, so 90 plus these other 5 on this other end here being higher. So that's the value we ended up having to use, and then ended up having to obviously make our shotcrete thickness work with this lower value, which obviously makes it thicker, right? So what we did in the next project, so obviously just highlighting here what happens is, besides a number of non-conformances, there were that we had to address in the follow-on project. There was also this change in requirements that we could no longer rely on adhesion. So the previous reliance on adhesion also helped us, because it means that if we could rely on adhesion, we flexural failure is not a viable, is not a possible mechanism. So this changed in the process of these initial projects. And there was also another requirement that, again, this is not even discussed, for example, in the empirical design by Barton, for example, is that there was also a requirement that we had to design our thin shotcrete lining for like huge fire exposures of 4 hours ISO curve, for those who are familiar with fire design, or even 2 hours hydrocarbon curve. So when you add this requirement here that we can no longer rely on adhesion, and this requirement to design for fire, it was putting a lot of pressure in our shotcrete design, and we had to then make our shotcrete work better in terms of flexural resistance. So we really had to satisfy that 3 MPa that in these first couple of projects we couldn't satisfy, even with a reasonably good fiber. So that's when we started looking at a high performance fiber. And why is a high performance fiber? You can see that the change in the end hook here shape has changed. So you have another fold in the end hook here. This provides a better embedment, a better pull-out strength of the individual fibers, and the tensile strength of the fibers also increased significantly. So from 1,300 and something that we had before, we went all the way up to 1,850 MPa. So a significant increase in strength in the steel for these fibers, and a significant improvement in the pull-out performance of these fibers by having a better embedment, right? So I have avoided here using the commercial term, obviously, but so for example, this fiber here is what is called the 4D fiber by drum mix. So it's a high performance fiber, and it was never used in shotcrete before. Common in TBM design and segmental lining, but was never used in, certainly not in Australia. And we tried to find in the world. I think we heard that has been used, but certainly in Australia had never been used before in shotcrete. And we decided, well, let's give it a go. Let's adopt this, and it's more expensive. But what it resulted is that with this better fiber, we could reduce the dosage of the fiber. So we tried even 45, if you remember what I mentioned. We managed to drop it back to 35, and the saving in the amount of fibers here was paying from the cost difference. And more importantly, we were achieving results that were much closer to the 3 MPa here. So for example, this is again the characteristic value here. We were achieving characteristic values of 283% on the beam testing, right? It's not quite 3 yet, but this value is acceptable because the codes recognize that when you're doing testing where you're preparing samples in the field, like where you're preparing samples that use some of the construction methodology rather than just crushing cylinders for compressive strength, the codes typically accept a difference of about 15%. So this value here, although not exactly 3, it was still deemed compliant, and it was obviously much higher than the previous 2 MPa that we were achieving. So we moved to this high performance, and the next project, we used this for about 250,000 cubic meters of shotcrete, where this shotcrete was consistently achieving values greater than 3 MPa, and was achieving 2.83 MPa as a characteristic value, which means 95% of results were above this. So now that we managed to achieve the target that we wanted, this close to the 3 MPa that I mentioned before, we wanted to now investigate. Okay, now I can already make the lining thinner, but how can I make it even thinner? Well, or not even thinner. How can I make it work now with this extra requirement, for example, for fire and for not rely on adhesion? And we started investigating that aspect that I mentioned to you all before of the compression membrane action. How the lining, when deforming, will generate internal in-plane compression that will bring the bending, the flexural capacity up. So to start with, before doing testing, to start with, we obviously started looking at some aspects of the design and start doing some numerical assessments and numerical modeling. So the first aspect that we wanted to investigate too, which is very particular to Australia, to Sydney, is the interaction between our shotcrete and our rock bolts support. If you look at the very first few pictures that I showed before, I always show the rock bolt plates on top of the shotcrete, because this is the most common application. You apply a certain layer of shotcrete first, then you bolt, then you shotcrete it again. Okay, in Sydney, in Australia, we have a different practice for questions of productivity, where we always bolt first, right? So when we always bolt first, then you can understand that we no longer have the support of this plate here, and we need something else to create that support. So what we do is we use rock bolt face plates that have what we call handlebars, is structural steel that go out like this, and we with the intention of hooking up the shotcrete when it goes in here, and the failure mechanism was originally estimated to be something like this. Okay, so if you hook that shotcrete up here, but you can see that for the same thickness, we will already be losing some of that punching capacity here, because it's no longer coming all the way from the back. Here it's coming from inside the shotcrete, right? So we wanted to test the capacity of our shotcrete lining. We had to understand the capacity of this system here first. So we actually did some field tests where we simulate the pull-out of the rock bolts, which is similar to the inverse of those round panel testing, right? So we sprayed big concrete blocks, like you can see here, the formwork with the rock bolt inside, representing the rock bolt in the tunnel, and we shotcrete this in place. So this is shotcreted. It's not just concrete pour, it's shotcreted. And what we do is we turn it upside down, and we put a hydraulic jack and we load it up to try to pull it out. So there's a pull out capacity. of this shotcrete here, and we develop, we can understand what's the capacity, we can develop curves. It's like, I call these, I make this joke, it's like a Excalibur test. It's like someone, trying to remove the Excalibur sword from King Arthur from the rock here. So that's the test we are doing. We generate a number of tests here. This is just some of the results, only about 1, 2, 3, 4, 5 results, but we had more with different types of plates, with different configurations, and so on. And we identified that the maximum load that one individual plate like this could take would be in the order here of about 80 kilonewtons. Okay, and we also back analyze these with numerical modeling to understand the failure mechanism as well. One interesting thing we noticed, we test rock bolt plates that had this handlebar, and you can see here the handlebars a bit better in this picture. And we tested also rock bolt plates without this handlebar to see what was the benefit of the handlebar. And what we noticed, and we also confirmed with the numerical analysis, that the majority of the capacity for the rock bolt type that we are using weren't coming from the handlebar, was coming from the shotcrete encapsulation around this hemispherical dome of this head here, right? Both the rock bolt plates with and without the handlebar achieve the same peak capacity, but the main difference is that once the shotcrete failed, the rock bolt plate with the handlebar had ductility to keep continuing loading without too much significant drop, while the one without handlebar would achieve a peak capacity here and would immediately drop, right? So we investigated that the capacity is actually coming from the head pullouts, but the importance of the handlebar in this particular case here was to provide ductility. And we confirmed this with numerical modeling. We could see here that the handlebar, the mobilization of strength and plasticity around the handlebar only comes at very much larger deformation than the peak, and when the load has already sort of plateaued a little bit. So, confirming that the peak capacity was coming from the rock bolt dome. So what we did later is also, now we wanted to test, as I said, predict the capacity of our concrete lining. So we did some numerical modeling, right? Imagine that our roof is bolted like this, has a pattern of bolting, and we're going to investigate one bolt in the middle, very similar to the round panel testing, right? So this is, we can assume, we can understand that this, because it's regular pattern like this, we can take advantage of planes of symmetry, and we can simulate a single panel numerically, right? And imagine that the wedge, remember the wedge A that I showed in some of the pictures, is located here and it's deforming. So we load a numerical model with this and see the resistance of the rock bolt plate here. To do this numerical model, we calibrated the performance of our shotcrete against beam testing. So you can see here, we did this calibration here, and we investigate what will be the capacity of our lining. So we estimated the capacity of our lining when taking advantage of compression membrane action would be at about 280 kilonewtons of the shotcrete if there's no punching failure, while that simple design method, the Berry-McCreath, for example, was only predicting about 60 or 70, right? So when taking compression membrane action, we were observing an increase of about 5 to 6 times the capacity, and we wanted to take advantage of this. So numerically and based on simple testing, we proved that we had a high capacity because of membrane action. So our next step was to do field scale testing to prove that in the field we can also achieve this when we combine with the high performance fibers. So what we did, we created a test in the field where we would shotcrete a wall, and we would put a loading system behind the shotcrete. So we created a slot in the rock. It's just hydraulic pressure bags, those bags that sometimes are used to lift, heavy equipment, or even to lift debris, for example, in accident, or even to open, cars that have crashed. If you have seen those types of hydraulic pressure bags. So we put behind the shotcrete here. We force the shotcrete to be debonded from the rock here. So we put a fleece that makes it debonded, so it has to fail in flexure or punching. And then we load it. All right. So some pictures of the testing here. So here's the fleece, the geotextile, forcing the shotcrete to be debonded. the pressure bag slotted into the rock here. So you can see a hose that goes up here. This hose is seen here as well. Then we shockwave this whole face here. We had a few panels for this testing. We loaded and we checked, crack pattern, and we had a load a system here which could measure the deflection of the shockwave here, so we could actually create a load deflection curve of this field scale test here. And then as we see here, the results were somewhat consistent with our class A predictions of about 280 kilonewtons here. The differences here is difference in thickness. We didn't have a regular thickness. We have thickness that vary from 75 all the way up to 100. But then you look at the ones that are close to 90 millimeters is the one that we are trying to achieve, 90 millimeter thickness of concrete lining. They were achieving always above 320 kilonewtons. And why it was about 320 kilonewtons? Because this is the capacity of 4 rock bolt plates, right? So remember that our rock bolt plates pull out had only 80. So if you do 80 times 4, that's why we only achieving the 380. So we proved that our shockwave was not the weakest point, right? So we could make it as thin as possible because the weakest point was the rock bolt plates. And we did a series of back analysis, a series of further calibration using round panel testing as well. And here is one of these back analysis testing. Here again, we only model 1 rock bolt plates. And the difference why this one has a sudden failure is because in our model, we only have 1, right? While 1 rock bolt plate, which when it fails has nothing else to resist. While in reality, if you look at here, if these rock bolt plates fail, I have other rock bolts around the tunnel to resist, which means that the span increases, right? But you still have resistance on the other rock bolts, which in the case of our numerical model, it doesn't. And that's why you see this big drop, while the others, you see a ductile behavior. And we confirmed that all the failure by numerical analysis was indeed happening through the rock bolt plates here. So we checked that the plates were the likelihood is that our handlebars were yielding and stretching, and that's why we achieved that capacity. So just to conclude then, so the use of high performance end hook fibers was very effective in achieved high performance ground support here in Sydney. It became now the go-to mix design using these high performance fibers. We are using round panel test. We're consistently exceeding 500 joules of capacity, and also consistently achieving the residual flexure strength of approximately 3 MPa for the dosage of fibers we adopted, which is only 35 kilos. Obviously, production testing has only minor outliers, which is at 5% we typically expect. And these allowed, with the combination of compression membrane action, allow us to do permanent concrete linings that are relatively thin and even resisting fire design, so of 90 millimeters. The project ended up not using 90 millimeters. They ended up using 110, not because of not because of ground load requirements, but because of embedment requirements for other fixtures, for things that need to be hung from the shockwave in the long term. So these elements needed an embedment that was close to 90 millimeters, so they needed a little bit extra at the back to satisfy that embedment. So the thickness ended up being increased for practical reasons, but from a structural point of view, 90 millimeters would be sufficient. And this was assuming that the lining is unbonded, and it was demonstrated that this capacity was achieved both by numerical modeling and lab scale testing and also field scale testing. So the consideration of compression membrane action effect confirmed that the load bearing capacity of these linings were 3 to 6 times greater than those estimated by conventional design methods based on pure bending resistance. And this was a good, a good outcome for the project and a good outcome for all the other projects that have now followed, because we understand there was savings in thickness. So from a sustainability point of view, this was great. There was obviously economical savings because we managed to reduce the thickness, and even though the fibers are more expensive, we managed to use less fiber, but more consistently achieve the results that we wanted. So I think that's it, what I had to say. I just leave here my contact details if you wanted to shoot me an email. You can also probably more easily look me up on LinkedIn and find me there. And I'm more than happy to also answer any other question that we have now or even later too. I push it back to you, Ruchi.
Thank you, Dr. Oliveira. Does anyone have questions? You can raise hands or just type in the chat box if you want. So, Mr. Yachik has a question. How would you design? How would the design and testing process be affected by macro synthetic fibers instead of steel fibers?
Yeah. The In terms of compression membrane action, the use of macrosynthetic fibers would not change that significantly. It will still be able, obviously, to achieve because it's all about the deformation of the lining and how it cracks. So you still could take benefit. Um, the reason why we haven't used macrosynthetic fibers so far in permanent lining in here in Australia is two reasons. One is we are designing thin linings that has to resist fire. So you can imagine that under fire, macrosynthetic fibers will melt, while the steel ones won't melt. So that's one of the drivers. Also, questions around um, the creep effects. Macrosynthetic fibers rely obviously on a polymer, and polymers are known to creep. So this is something that still um, brings some of the economics behind macrosynthetics a little bit down. So that's one of like a second driver. Um, Obviously, as I said, macrosynthetic also have benefits. That has compared to steel, they have the benefit of not suffering from corrosion like we have on fibers. Which, by the way, in our design, we assume an amount of the shotcrete where the fibers corrode, so this thickness is actually removed from this. So the way the design process would change is that we could still use macrosynthetic fibers, but it would certainly affect fire design, because then the fibers melt, and wouldn't rely on the thickness of the shotcrete where the temperature exceeds the value that melts the fibers, which is not very big. It's only about 150 or so Celsius degrees. And obviously also would affect, in terms of reduction factors, would also be affected because I have to take into account creep. So one of the challenges we have with the fibers is that even the best microsynthetic fibers, I'm yet to see them consistently achieving that 3 MPa residual flexural strength. They are very good for lower flexure requirement. So if you set your flexure requirement at about two, even 2.5, they are much easier to handle. But at this higher performance end, I am yet to see one that will consistently achieve. They can achieve in average again, but not at a characteristic value of 95%.
Thank you. Any other questions? Dr. Manoj Varman is here with us. He has raised a hand. So,
Hello, 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 David. How are you doing?
Hey Manoj,
This
good to see you.
okay. Yes, I really, unfortunately, I missed most of it because I was at a project site in a project office. So I joined as soon as I could, and I enjoyed whatever I could hear you speak about. This is the last point that you very nicely summed up. Really, really happy to hear it from you about your take on macrosynthetic fibers vis-a-vis the steel fibers. So I won't bother you much on that, except that, as you know, there's a raging debate in the industry across the world, and driven partly or mainly by the lobbies that promote these fibers. Do you think that in the near future, foreseeable future, Australia is going to use macrosynthetic fibers for permanent lining?
I think possibly, yes, very possibly. We, as I said, we need to be comfortable with some of the adjustments that needs to be done. So, what I would see is that we wouldn't be targeting this high performance, which means we might require some some changes in the targets required by projects. Because what you probably missed at the beginning, I said that these high performance, for example, when you're looking at a residual flexure strength of FR4 equal to 3 MPa, is something that's it's commonly required by the local authority here. It's not even us, because from a tunnel perspective, I think we can always specify. Well, look, if I want to use a shotcrete that's say 2 or 2.5 MPa flexure strength, I can design for it. I'll adjust the thickness accordingly. But when you have something that comes as a requirement from the authority, we need to achieve, right? And it's difficult to achieve with macrosynthetic. So we would need that change. We would need the change also in agreement with reduction factors to accommodate creep. That, for example, that's something that at the moment we don't have this. I'll tell you very simple. I'll give a very simple answer. Every time we have to use fiber reinforced elements here, most of the reviewers that we have from the authorities here look at the old testing from the ACI fiber sort of GFRP guidelines, and they ask us to design for reduction factors of 0.14. So we only use 14% of the capacity of those fibers, which is very low and uneconomical. Fibers have moved a long way from that. So if we can agree what are the reduction factors that we need to apply to accommodate creep, yes, I do believe we will very soon start seeing it. There's benefits, right? With macrosynthetic fibers, right? For example, the finishing is a lot easier. You don't have the little fibers, steel fibers sticking out. So you may not need, you may not need smoothing layers, for waterproofing membranes and things like that, depending on your aggregate size. So I do believe. I think the big question mark now is what is the actual requirement and what's the factors that we're going to have to design for. But I think we will get there eventually.
Yeah, sure. But fire remains an issue, particularly in the highway tunnels.
Yes. This is a debate too, right? Like if you look at the fire guideline from the ITA, the Australian Tunneling Society, like it's clear that the most important aspect of a fire is that you maintain your tunnel stable globally, right? It's implicit in that you can have local failures of your shockwave line as long as your tunnel remains stable, right? So if you are able to accept that too, then you will be able to accept that those fibers you melt, you're gonna have to repair. But at the moment also we have this, we can't accept that you have local failure of the shockwave, so we have to satisfy. And yes, the macrosynthetic in fire is a challenge too.
Right. I asked that question, actually, I'm just winding up now, because we are told that the use of the synthetic fibers actually started from Australian mines. So it is Australia which actually started, and many of the people who are promoting this, they give examples of those mines which are not designed for 100, 120 years. So
Correct.
anyway, this discussion can continue. I don't want to take everybody's time. Thank you very much, David.
No, thanks, Manoj.
Thank you, Dr. Manoj, for your query. So, does anyone has any more questions? Okay, so thank you, Dr. Oliveira, for your wonderful webinar on this use of high performance fibers. I'm sure that your experience will be very useful for everyone and everyone has benefited as well. And if anyone has doubts, kindly forward it to us and then we'll get in touch with uh, get in touch with Dr. Oliveira and we'll post it on a platform. And I would like to inform that We have all our past webinars on our YouTube plat channel, and this will be uploaded shortly. And before signing off, I would like to request all to renew the membership to ensure timely benefits. And once again, I'd like to thank you, Dr. Oliveira, for sharing your experience. And thank you for joining. Have a great weekend and stay safe and happy tunneling.
Thank you, everyone. Thank you.
Okay. Bye.
Bye-bye.
Bye. Thank you.